Hello class. Alright, go ahead and get out your notes in logarithms. They got the pink cover. We're going to look at section 4.3, logarithmic functions. Before we get started on this, my suggestion is that you have two colors handy. It'll be nice when we get to the graphing. If you don't have two colors, you just have a pen or a pencil, you might be able to use some highlighters. And if you don't have highlighters, I have them in the shelf. Um, you can see there's baggies um, on the shelf towards my desk area. You may grab a bag. Please return it with the markers back in the bag if you choose to borrow one. Okay, also, excuse me, the homework is going to be page 253. You can see the problems there. You should write that down. I don't believe that's on your notes. Also, there will be a couple graphs, so you'll want some graph paper. Again, the graph paper is in the colorful folders by the shelf, or on the shelf, near the door. Okay, so let's get started. Again, we'll pause the video as needed, rewind if there are questions. I'm going to go through it, the lesson, and hopefully you'll have some work time after this lesson and the 4.4 lesson. All right, so let's take a look at these problems that are a little different. 2 to the x power equals 32. How would we solve that? Now this is different than any other problem we would have seen before because the special thing about this is the variable is in the exponent. Okay, how do you solve an equation with x in the exponent? The common mistake that people a lot of times want to try is they think they can divide by 2. Now that's not correct. So you'd get the answer of x equals 16. And if you tried 2 to the 16th power, it's definitely not going to be 32. It's going to be some really, really big number. So we can't divide by 2. Another thing, a common mistake people think is they can take the square root of both sides, the square root. And that is also wrong. That cancels out if you have a power of 2. We have a power of x. So what we want to do is we want to get rid of this base of 2. We want to get rid of that base. So the question is, how do we cancel out the base? Cancel out this base. Okay. And the answer is going to be involving logarithms. Right? Hence the name of this chapter or this section, logarithmic functions. So another thing we can do is we can guess and check. For this one, it won't take too long to guess and check, and you might even know it, but x works. 5 works, 4x. 2 to the 5th equals 32. All right, so that's kind of nice, but they don't always work out. Actually, more often than not, you'll get ones that don't work, like this, 2 to the x equals 100. Well, if you get 2 to the 6th, that equals 64. 2 to the 7th, that equals 128. So it's going to be some number, some power that's between 6 and 7 that works. You might want to try, let's see what's in between here, 2 to the 6.5. And that's approximately equal to 90.5. Right, so that's still too low. So then maybe, okay, let's try 2 to the 6.75. And that equals about 107.6. All right. I used a calculator for those, and then you could keep going. Okay, so it's a little less than 6.75, and this could be kind of tedious, but it is a way of doing it. All right, but logarithms will be the answer, and we're not gonna quite solve these. Excuse me, this type just yet. We're gonna get to that. All right, so exponential form versus logarithmic form. So exponential form, which we've seen, is b to the x power is equal to a. All right, so we did some fancy colors for a reason here. So now, over to the side here, logarithmic form. So an exponential form can be rewritten into logarithmic form. So log is the abbreviation we use for it. And now for a base, log base b, we write, this is called subscript. So it's written lower. Kind of like how a power, like the x on the exponential form, is in superscript, meaning it's written above the normal line. Subscript is written below. Okay, so log base b of a. So now here's where the a goes. Is equal to, and then our exponent. Oh, I used the wrong color for b. Is equal to the exponent, which is x. Okay. So basically, it's just a rearranging of exponential form. The way it's said is log base b of a is equal to x. Log base b of a is equal to x. All right, and over here, b to the x power is equal to a. All right. And with all this, it's good to know, just like we said with exponents before, b must be greater than 0, and b cannot equal 1 for both types of forms here. All right. If b is equal to 1, then it's really boring. It's not really exponential then. It's just a flat line. If b is less than 0, if it's negative, then it just doesn't work. Okay, we get lots of issues. Okay, let's practice converting. Oh, we got a joke here. All right. Oh, I think I did peek at this one. So logarithms. Some of you might, if you haven't heard of it, this might be what you thought of with a logarithm. See some of these guys banging on this log. And if they're banging on the log in a nice way, they might have rhythm, right? So logarithm. Get it? Nope. Trying to underline. Yeah, those guys are really, see, I can tell that they're in rhythm because they both have their stick down at the same time, right? They're ready to be in unison. Okay, anyway, that's not what a logarithm is. It is a way to undo an exponential function. So anyway, for right now, let's practice taking an exponential equation and switching it to logarithmic form. So 2 to the 6th power is equal to 64. So each logarithm has log in it. Now the base is what we write in subscript, so the 2 here is our base of the answer, 64, so of 64 is equal to the exponent, 6. So in a logarithm, the exponent is the answer. That's supposed to be an equal sign on this next guy. All right, so log base 4 of 4 is equal to the exponent, which is 1. All right, this next one, log base 5 of the answer of 1 is equal to the exponent of 0. All right, log base 5 of 0.04 is equal to the exponent, which is negative 2 point, or sorry, just negative 2. All right, and this last one, it doesn't have an answer for the x, or for the exponent, it's just x. So let's see what that'll look like. So log base 3 of 81 is equal to x. So this log base 3 of 81, that's equal to x. So this is the exponent All right. It is the exponent because x is the exponent of this problem up here. All right. So the logarithm is the answer to an unknown exponent. All right. So what is that equal to? What is x equal to in this case? Log base 3 of 81. So that's me saying over here, 3 to some power is equal to 81. Now actually there is a nice answer for this one. Anybody know it? X is equal to what? Well, 3 to the first power is 3. Right? 3 to the second power is 9. Hopefully we know all those. Now 3 to the third is 27. Some of you might remember that one. And 3 to the fourth actually does give us 81. So the x value here is 4. All right. Now let's practice converting logarithmic form into exponential form. This is going to be the way that we are using more frequently because logarithmic form is kind of confusing looking and we're not used to it yet, so it's nice to be able to refer to a form that we're used to, which is exponential form. Okay, so looking over here, log base 10 of 100 is equal to 2. So base 10, that's going to be my base over here. Remember that the answer to a logarithm is an exponent, so 10 to the second power, and that's equal to 100, which makes sense. All right, next one, log base 7 raised to the second power is equal to 49. Excuse me, I got a little bit of cough. All right, a base of 8, an exponent of -1, and that's equal to the decimal 0.125. And another thing, remember that a negative powers flip. So what that looks like as a fraction is 1 over 8. That's what 0.125 gets calculated as. That might be handy when you get into the homework, knowing that. Okay, anyway, base of 5, so it's this little 5 that I'm using right now, raised to the power of 1 is equal to 5. And that should make sense. And then a base of 12, let's change colors, base of 12 raised to the power of 0 is of course equal to 1. Anything to the 0 power is 1. All right. So there are some special properties of logarithms that we're going to take a look at here. So when your base and the exponential answer are both the same, so log base of b is going to always equal 1. Because when you convert that, that means b to the first power is equal to b. All right, so an example might be log base 3 of 3. Well, that means this 3 raised to some power must equal this 3. And the answer to that is 1. So whenever the base and the stuff inside the parentheses is the same, the answer is always going to be 1. Okay. Another one is if we have a logarithm of 1. Okay. This is always going to equal 0 because the only way to get 1, unless your base is 1, but remember, we said earlier that b cannot equal 1. So since b cannot equal 1, the only way to get an answer of 1 is to raise something to a power of 0, like we see here. So an example, log base, 17 of 1. That means that 17 raised to some power is equal to 1. Well, that only power that exists is 0. All right. Okay. So, did I skip something down here? No. Okay. Okay, I'm just gonna have to write it in here. Common logarithm. So common logarithm. So the common logarithm looks like this. Log of x. It's kind of weird. It looks at first like it doesn't have a base. We don't write the base in, but it does have a base. This is just to save us some time. It's kind of like how we don't write a 1 in front of x. Because the coefficient is 1, we know it's there. Or like we don't write a power of 1 on an x, because we know the power is 1. So what this is equivalent to is log, and you might guess that the base is 1, but it's not. It's base 10 of x. All right, so that's the common logarithm. We don't, if it's base 10, we don't write that base in. Okay, so those are equivalents. Okay, so it's an unwritten base of 10. And it's called common logarithm because it is commonly used in applications. So in like real life applications, we like to use base 10. All right, a lot of times logarithms are used when calculating decibels. That's how loudness, so how loud something is. You might have heard of decibels. It also is used for the pH scale. If you've taken some science classes that talk about that, you hear about pH. There are things that are basic and there are things that are acidic. And something that we use to help calculate those are logarithms. And we use base 10 for both decibels and pH scale often. So anyway, so it's basically just base 10 and we don't write it in. All right, so let's try these using mental math. Now, you might need a calculator to just double check your work. Whenever we are doing these mental math ones, what I really want you to be able to do is convert these into exponentials first. So I want you to show that you can convert it, because it's like we don't know what this is equal to, this log of 1,000. And it's a common logarithm because notice that there's no base here. But let's set it equal to x. So now it's a logarithmic form. How would we convert that into exponential form? Well, since we know that there's a 10 in the base there, it's base 10 raised to the power of x. It's equal to 1,000. Now this might help us solve it mentally. If you remember the trick when raising a power of a 10 to a power, it's just how many zeros there are. So 1, 2, 3. This is 3. 10 to the third power. Now we can double check that by using our calculator, typing in 10 to the third power, and we should get 1,000. All right, same thing as over here. This is set equal to x. Again, we have a base of 10 because there's no base written. So this 10 to the x power is equal to 0.001. Okay. Now that one might be a little trickier. I know that if it's a decimal, it's probably gonna have to be a negative exponent. Another way to look at this is, what is this as a fraction? Well, it's gonna be what? This is tenths, hundredths, thousandths. So it's 1/1000th, if that helps. So that means it's negative because it's been flipped. And well, how do you get 1,000? Well, that's the third power, so x would be equal to -3. Because 10 to the third, as we saw before, is 1,000. Since it's 1/1,000, that must be a negative exponent. All right, and the way I remember how we do these, this is tenths place, hundredths place, thousandths place. That's how I converted it into the fraction. All right. Let's take a look at log base 4 equals 1/4. So now we know the base is 4. Let's set it equal to x as an unknown. So that means 4, this base of 4 to the x power is equal to 1/4. All right, this is kind of like the last one we just did. It's a fraction. So it's going to be a negative. And so flipped it, 4, well, 4 to what power gives us 4 is just 1. So it's negative 1. And we can double check that. 1/4, the calculator might tell us 0.25, which is the same as 1/4. But that's what it is. Excuse me, sorry. Okay. All right. Now, this next one, set it equal to x. Base of 5 to the x power is equal to 625. All right. So this one, I don't know. You might be able to get it by doing it mentally, but I would verify with a calculator. We know that 5 to the second is 25. You might know that 5 to the third is 125. And if you think about it, okay, well, 5 to the fourth is multiply 125 by another 5. Well, 100 times 5 is 500, but it's more than 100, so I don't know. It makes sense that this would be the next thing, and you can verify that on a calculator. So anyway, that means that x is equal to 4. Okay. All right. So you will get a couple of those in the homework. Now, for graphing, this is where 2 colors will be helpful. Okay. We're going to graph an exponential function and its inverse, which is a logarithmic function. Okay. So the function y equals 2 to the x, the logarithmic form of that is going to be y equals log base 2 of x. Okay. All right. So to be able to graph an inverse function, remember that you can just reverse all the x's and y's of its original function. Now we can find some points of the function y equals 2 to the x. And then we can use that to help us find the inverse functions. So here I'm going to go red with exponential and blue with logarithmic. So first let's make a table for y equals 2 to the x. All right, so x, y, we'll do a couple of these. Let's go -1, 0, 1, 2, and 3. Well, don't overthink negative first power. You can do this on a calculator, remember, as well, but if you raise it to the negative first power, 2 to the, that just flips it, so 1 over 2, or 1/2, or 0.5. To the 0 power, that's going to be 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So let's go ahead and plot those points. So -1 up a half, 0, 1, 1, 2, 2, 4, and 3, 8. All right. Connect those and make sure you don't cross that x-axis. All right, there's our exponential function. Now, remember the fact that an inverse function reflects about that line y equals x. And it's that diagonal line. It goes through all of these points. That's that line y equals x. So all these points are going to reflect over it. And sometimes that can be confusing for people. I don't know, I kind of like doing it this way sometimes. So like this point, 1, 2, I see that it will easily reflect right over there. And you just think of it as a mirror. They've got to be the same distance. If you like doing it this way, that's great. Otherwise, we can make a table for the logarithm. And we're going to basically focus on the exponential table that we just made, and we're just going to flip-flop the x's and y's. So this becomes 1/2, -1. 1, 0, 2, 1, 4, 2, and 8, 3. And we can plot those points. And I've already plotted two of them. I've plotted 1, 0, and what is that, 2, 1. Okay, so 1/2, -1. So over a half, down 1. So that'd be about there. Okay, and then over 4, up 2, right here. Over 8, up 3, right there. Okay, and notice that it should have a similar shape to the original function. So it's going to curve down, and then this one shouldn't cross the y-axis. So the red function doesn't cross the x-axis, this guy doesn't cross the y-axis. Now, what about domain and range of these guys? So, for the red, the exponential, domain, I'll just use D for domain, it's going left forever and slightly to the right forever. It's going to have all real numbers. And its range is, it goes up forever, but it doesn't go down forever. It can't go into the negatives, and it actually can't even hit 0. It's never going to hit this x-axis. So the y values must be greater than 0. Now for logarithms, remember, domain and ranges flip. So domain is going to be, actually x is greater than 0. And you can see that should make sense by looking at the graph. It doesn't go to the left forever. It doesn't touch the y-axis, but it does go to the right forever. So it's going to get to have really big positive answers. And then the range, how high and low it goes, well, it's going up gradually forever, and it's going down pretty quickly. So that's going to hit everything. That's all real numbers. Okay. Let's take a look at another exponential and logarithmic. So, why are you drumming on your algebra book with two big sticks? That kind of sounds like the cartoon. I'm guessing it has something to do with logarithms. Let's see. Because we are studying logarithms. Ah, okay. Logarithms, yep. Okay. Let's keep moving. Graphing logarithmic functions. So use the given x values to graph each function and graph its inverse. Describe the domain and range of the inverse function. Okay, so they're giving us this original function, f of x equals 3 to the x power. On the homework, they'll give you something like this. Then they'll give you a list of x values like this. We've already calculated out those powers for you in this table. You'll have to do that on your own in the homework. And we can go ahead and graph those. So 2, 1/9, that's pretty far down here. Or sorry, -2. -1, 1/3, it's a little higher up. 0, 1, 1, 3, 2, 9. We can go ahead and graph that guy. Let's call it f of x. Okay. And all right, then we can graph the other guy. So we can just flip-flop all these. 1/9, -2. 1/3, -1. 1, 0. 3, 1. 9, 2. Again, we could just reflect it over that diagonal line, y equals x, because that is a key feature of inverse functions. I feel like most people will like to just plot the points, but either way works. So over 1/9, so barely over, and then down 2. Over 1/3, down 1. Over 1, up 0. Over 3, up 1. Over 9, up 2. And don't cross that y-axis. And that is the function. Let's label that f inverse of x. Now the homework will not ask you to write the inverse function, but I challenge you to do that. So basically it's just whatever the base is, make sure you write it as log base that number. So in this case, base 3. And let's not forget domain and range. So domain and range of, yeah, I'll just use colors. Red is my exponential one. So domain is all real numbers. Range of the exponential one is y values are greater than 0. For logarithms here, for the logarithm, the domain is x values are greater than 0, and the range is all real numbers. Notice how the domain and range are kind of flip-flopped, not 100% because of these two guys. You have to convert from y to x when you do the inverse. All right, let's take a look at one more. Okay. So again, we have this function 0.8 to the x power. It gives us these x values to use. We calculated out the y values that we get from them. So -3, it's kind of off the graph a little bit here, but up 2, then 0, up 1. Oh, I'm sorry, I was using red for exponentials. 1 up 0.8, 2 up 0.4. Oh, no, that's wrong. That's not 2. That's 1 up 0.8, 4 up 0.4, and 7 up 0.2. So we've got a very gradual curve here, like so. That is f of x. All right, let's go ahead and draw in that diagonal line again. Make it dashed because it's really not part of what we're graphing. So this one's going to be a little different. So this is an exponential decay. So let's see what happens with logarithmic ones. So we'll reflect all these. So 2, -3, 1, 0, 0.8, 1, 0.4, 4, 0.2, 7. Okay. So let's go 2, -3, 1, 2, 3, about there. 1, 0, right here. 0.81. Let's see if I can fit that in there. About there-ish. 0.4, up 4, about there. 0.2, up 7, about up there. Graph this guy. Do not cross the y-axis. Oop, kind of started veering off there. Okay, let's start that again. Okay. Okay, not much of a curve. It almost feels like you're drawing a straight line, but it is curving up, or to the right. So that is f inverse of x. All right. And they should all three, the green, the red, and blue, notice that they all cross in that same spot right there. And that should have been true in the last one as well, actually. Well, actually, they don't cross, so it's not true in this case. But if they do cross, they all three should cross in the same spot. That's another clue that you're doing it correctly. I think it will really help if you're using two different colors, or at least highlight one of them, or highlight each one a different color. All right, let's talk domain and range. So domain of the exponential is all real numbers because it's going left and right forever. Its range are y values that are greater than 0. Even though it's decay, its range and domain are the same as what they were when it was exponential growth. Okay, so then for the logarithm, the domain is all x values that are greater than 0. And the range, the y values, it goes up forever and down forever. All real numbers. All right. And that is 4, 3.